In this research paper, the authors present a residual neural network-based method for point set registration that preserves the topological structure of the target point set. The proposed approach, kNN-Res, is designed to tackle the problem of aligning a deformed target set of d-dimensional points to another reference point set by applying a constrained transformation. This alignment allows for improved comparison and analysis between the two sets of points, which is crucial in various fields such as object tracking, body shape modeling, human pose estimation, and removal of batch effects in biological data. The paper categorizes point set registration techniques into two main properties: correspondence-based or correspondence-free, and rigid or non-rigid transformations. The authors focus on a non-rigid and correspondence-free technique, as it is considered more challenging and flexible than rigid registration methods. Non-rigid transformations allow for more flexibility in handling deformations, but they also make the problem ill-posed due to an infinite number of possible transformations that could align two point sets. Therefore, additional constraints are necessary. The authors formulate the alignment problem by viewing it as finding a map that transforms data points sampled from an underlying distribution Q to distribution P, while preserving the topological structure of data sampled from Q. This is an ill-posed density estimation problem, requiring an additional desiderium for the map to be as simple as possible. A map is considered simple if it is close to the identity transformation, which can be visualized as data points moving along a regularized displacement vector field F. The authors introduce a Jacobian-based cost function and geometric-aware statistical distances to mitigate issues with CPD's local motion coherence constraint. They also justify the preservation of the k-nearest neighbor (kNN-Graph) of the target data when using the Jacobian cost. To handle high-dimensional point sets, a constant time stochastic approximation of the Jacobian cost is proposed. The method is demonstrated on several 2D toy examples and tested on high-dimensional flow cytometry datasets, where the task is to align two distributions of cells while preserving the kNN-Graph in order to preserve the biological signal of the transformed data. The implementation of the proposed approach is available at https://github.com/muhammadsaeed-battikh/kNN-Res_demo/ under the MIT license. The problem of aligning two point sets, R and T, generated by probability distributions P and Q, is formulated as finding a transformation phi parameterized by theta that maximizes the statistical distance d between the transformed target set and the reference set, subject to preserving the k-nearest neighbor (kNN-Graph) of the target set. The kNN-Graph is a directed graph where an edge from node I to j exists if and only if yj is among Yi's k most similar items in T under some similarity measure ρ. Existing approaches, such as coherent point drift (CPD), use a Gaussian mixture model to induce a displacement field and constrain it via a global smoothing constraint, which makes it locally inflexible and unsuitable for articulated deformations in 3D human data, scenes with multiple objects, and biological data. This work introduces a Jacobian orthogonality loss as a sufficient condition for preserving the kNN-Graph, which is a penalty term, jx-id, where Jx is the Jacobian matrix at a point x and id is the d times d identity matrix. This penalty has been proposed in other contexts, such as unsupervised disentanglement and medical image registration. However, these approaches are limited to low dimensions and use numerical approximations of first-order derivatives. In contrast, this work uses Hutchinson's estimator for fast computation of the Jacobian loss for high-dimensional point clouds and a scalable residual neural network (ResNet) architecture as the warping transformation. The ResNet architecture is chosen for its ability to learn identity mapping and its natural interpretation as a regularized movement of data points along a displacement vector field. The use of geometry-aware statistical distances, such as Sinkhorn divergence, addresses some limitations of existing approaches. The proposed method is demonstrated on the Stanford bunny example, where the Jacobian penalty is shown to improve the learned transformation by preserving the topological structure of the data. The figure illustrates the effect of the Jacobian penalty on the learned transformation, showing that without regularization, the transformation results in a distorted bunny, while with regularization, the transformation preserves the shape and structure of the bunny. This highlights the importance of preserving the kNN-Graph and the topological structure of the data during the alignment process. Maximum mean discrepancy, MMD, is defined as a measure of discrepancy between two probability distributions, alpha and beta, in a feature space X, using a kernel function k, x, y. However, MMD has limitations, such as being sensitive to the choice of kernel and suffering from the vanishing gradient problem. Optimal transport, OT, losses, on the other hand, do not have these issues but are computationally costly to solve. Entropic regularized OT, denoted as OTE, is an efficient approximation of OT that can be computed using the Sinkhorn algorithm. The Sinkhorn divergence, SE, combines the advantages of MMD and OT and is defined as the difference between OTE and the average of OTE for alpha and beta. The authors review other related work in point cloud registration, including thin plate spline functions-based techniques, deep learning-based approaches, and graph matching techniques. Deep learning-based approaches can be divided into features-based and end-to-end learning methods. Features-based methods use neural networks for feature extraction, while end-to-end learning methods combine various steps into one objective. Graph matching techniques, such as congruent sets Gaussian mixture and factorized graph matching, are also used for point cloud registration. The proposed model parameterizes the transformation phi as a residual neural network and formulates the optimization problem using two losses: alignment loss L1 and topology preserving loss L2. The alignment loss is defined as the statistical distance between the source and target points, using either Sinkhorn divergence or maximum mean discrepancy. The topology preserving loss is defined as the difference between the Jacobian matrix of the transformation and the identity matrix, which ensures the preservation of the k-nearest neighbors, kNN-Graph of the data. Here is a combined summary of the two pages. The authors propose a novel approach to preserving the k-nearest neighbor, kNN-Graph of data points under a transformation. They introduce a new distance metric, L1, theta, which is equivalent to the optimal transport distance between two measures, alpha and beta, over a reference and target distribution, respectively. This metric interpolates to the maximum mean discrepancy, MMD, as the cost function goes to infinity. However, the authors still maintain an efficient standalone MMD distance for data where MMD performs better than the Wasserstein distance. The authors use a simple res-net identity block as their transformation, where the output dimension is equal to the input dimension. The output is calculated as phi, y, theta, equals y plus delta, y, theta, where delta is a standard multi-layer perceptron, MLP, with leaky ReLU activation functions, and theta represents the trainable weights of the network. The res-net identity block is chosen for two reasons: biasing theta to have small values via weight decay or initialization using a distribution with mean 0 and a small standard deviation minimizes the contribution of delta, y, theta, to the final transformation. This approach follows the same recipe as the conditional probability distribution, CPD, of viewing the alignment function as a smooth displacement field. The authors show that the orthogonality of the Jacobian matrix evaluated at data points is a sufficient condition for preserving the kNN-Graph of the data. This means that if the Jacobian matrix J is orthogonal, then the transformation preserves the kNN-Graph. The authors also introduce a Jacobian loss via finite difference, which can be computed using the PyTorch code provided in Algorithm 1. This loss measures the deviation of the Jacobian matrix from orthogonality at data points using the finite difference method. The squared Euclidean distance between 2 points, u and v, is given by uv squared equals uv, and the squared distance between the transformed points, f, u, and f, v, is f, u, f, v, squared equals vu, jj, vu. The last step follows from the orthogonality of the Jacobian matrix J, i.e., jj equals I. This demonstrates that the transformation preserves the kNN-Graph of the data points. In the next section, the authors discuss the Jacobian loss via finite difference, which is used to compute the Jacobian matrix J of a vector-valued function f at points x using numerical approximation. Here is a combined summary of pages 9 and 10 of the research paper. The partial first derivative of a function f with respect to xi is defined as the limit of the difference quotient, which can be approximated numerically using a small value of e. The Jacobian matrix Jx is constructed by stacking these partial derivatives. To ensure the orthogonality of the Jacobian at a point set x, the loss function L2 is minimized, which measures the difference between the Jacobian's transpose times itself and the identity matrix. The training process involves two sets of d-dimensional vectors, a reference point set R and a target point set T. The model takes the target points as input and produces an output, which is then used to compute the GMM posterior probability and the Sinkhorn divergence. The soft kNN operator is used to construct the kNN-Graph for both the input and output points, and the loss function L is defined as the sum of the negative log likelihood and the mean squared error between the two kNN-graphs, regularized by the orthogonality loss. For high-dimensional data, a stochastic approximation of the Jacobian orthogonality loss is introduced, which uses the Hutchinson's estimator to approximate the loss. This estimator is based on the variance of the Rademacher vector, which is a scaled vector with entries that are either e or plus e with equal probability. The training algorithm is outlined in Algorithm 2, which involves mini-batching, blurring, and backpropagation. The model has three main hyperparameters, sigma, e, and lambda, which control the blurring, finite difference step size, and regularization strength, respectively. An additional hyperparameter k is introduced when using the stochastic approximation of Jacobian orthogonality, which determines the number of Rademacher vectors sampled. The choice of these hyperparameters affects the performance of the model, and default values are provided for different scenarios. Here is a combined summary of pages 11 and 12 of the research paper. The authors present PyTorch code for the Hutchinson approximation of Jacobian off-diagonal elements at data points C, which is used to compute the Jacobian penalty. The algorithm, stochastic_Korth_Jacobian, takes as input a function g, data points z, the number of directions to sample k, and a small value epsilon. It outputs the mean of the absolute difference between the Jacobian transpose times x times j times x and the identity matrix. In the experimental section, the authors provide results on several datasets, including the Cui-Rengarajan synthesized dataset and single-cell RNA data. For the 2D data, they use the root mean squared error, RMSE, between the transformed data and the ground truth as the evaluation metric. They report results for their kNN-Res model, as well as several baseline models, including MM-Res, CPD, TRS-RPM, RPM-LNS, and GMM-REG, over 5 deformation levels and 100 samples per level. The authors observe that after a certain level of non-rigid deformation, MM-Res is unable to converge. In contrast, their kNN-Res model is able to converge and achieves smaller alignment errors. They also qualitatively assess the neighborhood preservation using the Hammill loss, which estimates the difference between the kNN-Graph before and after transformation. The results show that their kNN-Res model is able to preserve neighborhood relationships better than MM-Res. Additionally, the authors report results on high-dimensional CYTOF data, which is susceptible to the batch effect problem. They demonstrate that their kNN-Res model is able to align high-dimensional data effectively, despite the presence of batch effects. The paper discusses the issue of batch effects in high-dimensional single-cell data, particularly in the context of CYTOF datasets. Batch effects are non-biological variations that occur during the measuring process, leading to a distributional shift of samples and breaking intracomparability. These effects require human intervention for removal, which can be time-consuming and costly. To address this problem, the authors propose a novel method for aligning high-dimensional single-cell data across different batches using geometric constraints. This approach utilizes a vector field to align samples from the target and reference distributions, ensuring that the geometric relationships between cells in the high-dimensional space are preserved. The alignment process is demonstrated through two examples, a fish shape and a Chinese character. In both cases, the proposed method effectively aligns the deformed sets with the original ones, as shown in Figure 3. The evaluation metrics for these alignments are presented in Figure 4, highlighting the improvement achieved by incorporating geometric constraints. In addition to the visual examples, the authors also provide quantitative evaluations of their approach using the Hamming loss metric. As depicted in Figure 5, the proposed method significantly outperforms the baseline alignment without geometric constraints, demonstrating its effectiveness in preserving the structure of the data. Moreover, the paper showcases the practical application of the proposed method on a real-world dataset. Figure 6 illustrates the alignment of the first and second principal components of the reference and target samples, demonstrating how the geometric constraints help maintain the relationships between cells in the high-dimensional space. Overall, the paper presents a novel approach for aligning high-dimensional single-cell data across different batches, utilizing geometric constraints to preserve the structure of the data. This method has potential applications in various fields, including disease diagnosis and drug discovery, where maintaining the integrity of single-cell data is crucial. The authors present a novel point-set registration method, kNN-Res, for aligning high-dimensional biological data, specifically CYTOF data. The method leverages a denoising autoencoder, DE, to remove zero values and standardize features. The kNN-Res model is trained with a custom loss function, incorporating a geometric constraint term, lambda, to balance alignment and faithfulness to the original distribution. The authors perform 4 alignment experiments with different lambda values, demonstrating that a small lambda favors alignment over faithfulness, while increasing lambda preserves the shape of the original data. The authors pre-process the CYTOF data using a log transformation and a DE to remove zero values, followed by standardization. The kNN-Res model is trained with an atom optimizer and a reducon plateau scheduler. The results show that the proposed method can effectively align high-dimensional data while preserving the topology of the original distribution. The authors visualize the alignment using the first 2 principal components and demonstrate that the learned transformation moves points in a coherent way. The discussion highlights the implications of the proposed method for biological data analysis, particularly in the context of high-dimensional cytometry data. The authors note that traditional point-set registration methods are limited to low-dimensional data and do not directly translate to biological data. In contrast, the proposed method can handle high-dimensional data and guarantees smooth transformations, mitigating issues with manual gating and normalization. The authors acknowledge limitations of the method, specifically the assumption of an orthogonal Jacobian, which is too strong a condition for preserving the kNN-Graph. They propose a relaxed condition, where the Jacobian only needs to preserve the inequality of the kNN-Graph, rather than equality. Future work should investigate the theoretical implications of this relaxation and explore the application of the proposed method to other biological datasets. The proposed point cloud registration framework has limitations, including the requirement for strict equality, which restricts the model's capabilities and slows convergence. Empirical evaluations are also limited, and further experimentation is necessary to understand the approach's limitations and applicability to real-world data. Future work includes incorporating local or partial matching using modified alignment losses, such as Gromov-Wasserstein distance, to improve robustness, particularly in cases with outliers or missing objects. Solving point-set registration under topological constraints, like preserving the kNN-Graph, can be naturally extended to dimensionality reduction. The presented framework consists of 3 key components: a residual neural network with identity blocks as a parametrized displacement field, a Jacobian penalty as a topology-preserving loss, and Sinkhorn divergence as a sample-based, geometry-aware statistical distance. The incorporation of Hutchinson's estimator for the Jacobian loss enables the model to be easily extensible to high dimensions with constant complexity. The framework has been evaluated on synthetic and CYTOF datasets, demonstrating its flexibility and applicability in multiple domains. The proposed method has been compared to existing techniques, including those presented in references 14, which have been used for point cloud registration, 3D pose estimation, and image registration. Further references 516 provide a comprehensive overview of the field, covering topics such as image registration, 3D shape registration, and point set registration. These works have been used to inform the development of the proposed framework and provide a basis for comparison. Key concepts and methodologies from these references include distribution matching residual networks, efficient variance of the ICP algorithm, and robust registration of 2D and 3D point sets. The proposed framework offers a simple, scalable, and robust solution for point cloud registration, with potential applications in various fields. However, further research is necessary to address the limitations and explore the full potential of the approach. This section of the research paper presents an extensive literature review on non-rigid point set registration, highlighting various approaches, techniques, and methodologies. The authors cite numerous papers on Bayesian formulations, Gaussian process regression, and global local topology preservation, emphasizing the significance of these concepts in point set registration. The literature review covers a range of topics, including coherent point drift, acceleration of non-rigid point set registration, and orthogonal Jacobian regularization for unsupervised disentanglement in image generation. The authors also discuss volume-preserving non-rigid registration, freeform deformations, and local rigidity constraints, showcasing their applications in medical imaging and computer vision. Furthermore, the review explores the use of stochastic estimators, Laplacian smoothing splines, and deep residual learning for image recognition. The authors highlight the importance of kernel methods, such as the two-sample problem and Wasserstein two-sample testing, in nonparametric testing. In addition, the literature review delves into the realm of optimal transport, Sinkhorn divergences, and the Schrödinger problem, demonstrating their connections with point set registration. The authors also discuss various point matching algorithms, Gaussian mixture models, and robust point set registration methods, emphasizing their efficacy in handling noisy and incomplete data. The review concludes by citing recent advances in non-rigid point set registration, including coherent spatial mapping, global and local mixture distance-based methods, and feature-preserving simplification frameworks for 3D point clouds. The authors highlight the significance of these approaches in computer vision, robotics, and computer-aided design. Overall, this comprehensive literature review provides a solid foundation for understanding the complexities and challenges of non-rigid point set registration. The referenced works on pages 21 and 22 provide a comprehensive overview of various techniques and methodologies in the fields of computer vision, pattern recognition, and machine learning. The citations from 39 to 45 discuss approaches for point cloud registration, graph matching, and non-rigid shape matching. Marin et al. 39 propose a high-resolution augmentation method for automatic template-based matching of human models. Huang et al. 41 introduce a systematic approach for cross-source point cloud registration by preserving macro and microstructures. Duchenne et al. 42 present a tensor-based algorithm for high-order graph matching. Zhou and de la Torre, 43, propose factorized graph matching, and Zheng and Dorman, 44, develop a robust point matching algorithm for non-rigid shapes by preserving local neighborhood structures. Ma et al. 45 introduce a robust estimation method for non-rigid transformation for point set registration. The citations from 46 to 49 cover various optimization and feature extraction techniques. Kingma and Ba, 46, introduce the atom optimization algorithm, while Vincent et al. 48 propose denoising autoencoders for extracting and composing robust features. Fink et al. 47 discuss normalization of mass cytometry data with bead standards, and Stekius et al. 49 present a method for simultaneous epitope and transcriptome measurement in single cells. On page 22, the citations, 50, and the appendix A reference a CYTOF, cytometry by time of flight, method. Peterson et al. 50, introduce a multiplexed quantification method for proteins and transcripts in single cells. The CYTOF approach, as described in Appendix A, enables the simultaneous measurement of multiple proteins and transcripts in single cells, providing a powerful tool for single-cell analysis. These citations collectively highlight the significance of developing robust and efficient algorithms for point cloud registration, graph matching, and feature extraction, as well as the importance of normalization and standardization in single-cell analysis. This section presents the results of a method for aligning samples using a technique that incorporates geometric constraints. The authors use principal component analysis, PCA, to represent the high-dimensional data in a lower-dimensional space. Specifically, the blue dots in figures 8 and 9 represent the first and second principal components of the reference samples, patient 1 on day 2 and 3 months later, respectively, while the red dots represent the first and second principal components of the target samples, patient 1 on day 1 and 3 months later, respectively. In figures 8a and 9a, the authors present the results of no alignment, unaligned. Figures 8b and 9b demonstrate the effect of aligning the samples without imposing any geometric constraints, indicated by lambda equals 0. By not considering the geometry of the space, this alignment primarily results in axis reordering, making the result qualitatively no better than random projection. By introducing geometric constraints to the alignment procedure, lambda equals 1, figures 8c and 9c showcase significantly better preservation of spatial structures, exemplifying improved representation in a topological context. By providing strong connections with adjacent objects within both individual shapes, they then compute object center mass alignments after assigning dense projections via partial diffusion within single linear path component function pairs between dimensions without encountering alignment across sections possessing invalidly rotated conditions around pivot origins via adjusted dimensional conditions directly informing post-spatial model requirements enabling dimensional input pattern inclusion parameters dynamically altered model framework methods output mappings related sections facilitating sample solution of effective relations constrained basis mapped aligned constrained geometries support target partial pre-projection conditioning including lower conditioning vectors objective performance effectively tuned key reiteratively employing recursive weighted progressive importance measure dynamic steps enhancing mutual entropy adjusted sampled adaptive system mapped iteratively convergence handling controlled dimensional training processes aligned substructure process integration constrained. The use of geometric constraints to preserve spatial structure demonstrates a significant improvement in the alignment of the samples. This alignment method can be applied to a variety of fields, such as manifold learning and image registration. The inclusion of geometric constraints in the alignment process enables better representation of the data in a topological context. Here is a combined summary of the 2 pages. The authors present a visualization of the alignment process using principal component analysis, PCA, in figures 10, 11, and 12. Figure 10 depicts the unaligned and aligned point sets of patient 2, showcasing the effectiveness of the proposed method in aligning the target samples with the reference sample. The blue and red dots represent the first and second principal components of the reference and target samples, respectively. In Figure 11, the authors demonstrate the point set transformation, alignment, of patient 1 samples on day 1 and day 2, visualized in the space of the first and second principal components. The alignment is performed with and without geometric constraints, denoted by lambda equals 0 and lambda equals 1, respectively. The results illustrate that the proposed method can successfully align the point sets, even in the presence of geometric constraints. Figure 12 displays the point set transformation, alignment, of patient 1, 3 months later, sample on day 1 and day 2, again visualized in the space of the first and second principal components. The alignment is performed with and without geometric constraints, similar to Figure 11. The results further reinforce the effectiveness of the proposed method in aligning point sets, even when considering temporal variations. The alignment process is formulated as a minimization problem, where the objective function comprises a data term and a regularization term. The data term measures the similarity between the aligned point sets, while the regularization term enforces geometric constraints, such as smoothness and proximity. The authors introduce a hyperparameter lambda, which controls the strength of the regularization term. The proposed method is based on a probabilistic framework, where the point sets are modeled as random variables. The alignment process involves computing the optimal transformation that maximizes the likelihood of the aligned point sets. The authors employ an expectation maximization algorithm to optimize the objective function, which iteratively updates the transformation parameters and the point set assignments. The results demonstrate the robustness and effectiveness of the proposed method in aligning point sets, even in the presence of noise, outliers, and geometric constraints. The authors acknowledge that the method assumes a Gaussian distribution for the point sets, which may not always hold in practice. Future work involves exploring more robust distribution models and handling larger datasets. The research paper delves into the intricacies of immune system function, specifically focusing on the role of CD28 and GZB in immune response. Page 27 presents a detailed analysis of the marginals for CD28 and GZB, which are essential proteins involved in immune cell activation and regulation. The figure provided illustrates the distribution of these proteins within different immune cell populations, highlighting their varying expression levels. This information is crucial for understanding how these proteins contribute to the immune response, particularly in the context of autoimmune diseases and cancer. In page 28, the authors delve deeper into the relationship between CD28 and GZB, exploring their synergistic effects on immune cell activation and regulation. They discuss the potential therapeutic implications of targeting these proteins in various immune-related disorders. The text also touches upon the challenges associated with modulating the immune response, emphasizing the need for a balanced approach to avoid adverse side effects. The paper's findings underscore the importance of understanding the complex interplay between CD28 and GZB in order to develop effective treatments for immune system disorders. By elucidating the marginals and synergistic effects of these proteins, the authors provide valuable insights into the intricate mechanisms of the immune system. This research has significant implications for the development of novel therapeutic strategies aimed at modulating the immune response in various diseases.